Oh my God, it is Hot Rod, Dr. Roddenberry, coming to you from Willow Springs, North Carolina. That better not be Leanne Politz, is it, Lauren Mahaffey? I think I know who you're talking about because I remember the person that gave me that nickname. Quite a character. Or maybe it's another one of her friends. It's good to see everybody. Thanks for coming to the lecture today. We are in the second module of Psychology 115. This particular module is called Hereditary Genius, and it consists of a couple of chapters that we're going to put together, namely the intelligence chapter and the research methods chapter. Ah, okay, it is Tyler. Okay, tell Tyler I said hello. Tyler must have been in that class because I do remember the class where I got that nickname and the cornball student that gave me that nickname. But very good. Tell Tyler I said hello, and he's always welcome to drop into these broadcasts and say hello. So, at any rate, I am here in Willow Springs, North Carolina, as I said, and for this module, we're going to be talking about research methods, and we're going to be talking about how research methods can be applied to a specific area of psychology. We're going to be talking about an IQ testing, okay? So the question is, how do we know something is true, right? So how exactly do we know that something is true? I don't know if you know this, but philosophers have always been interested in trying to figure out what it is that makes something true. Does anybody out there, can anybody describe what is it that makes something true? Is it our eyes? Is it our heart? Is it what we believe? Some people talk about truth in a science lab. Other people talk about truth in religious movements. What exactly does it mean to say that something is true? I don't know if you folks know this, but there is even a branch of psychology known as epistemology. Epistemology, that is interested in the search for knowledge. If you've ever taken a logic class and talked about if P, then Q, if not P, then not Q, and done any of those logic tests or Venn diagrams before, you know what I'm talking about because that's epistemology. And they're interested in the truth. And so that we're going to be talking about how we as scientists, as psychologists, develop knowledge about human beings that are true. I don't know if you folks hear every day people are talking about fake this, fake that, this is true, that's true, fake news, true news. What does it all mean? And it's very conflicting trying to figure out exactly what is true from what is not true. In psychology, because we talk about human functioning, a lot of times we talk about topics that are very sensitive and very political, and very open to bias. So it is very important for us as psychologists to understand what it means to search for the objective truth. And what I'm going to do for you folks today or this semester is I am going to try to tell you everything I know that is true. There is no time this semester where I'm going to try to deceive you or tell you something that I don't believe in 100%. Now, I'm not the arbiter of truth, and so there are other people who know things that are true too. Sometimes what is true in knowledge is an evolving process. 2 years ago, I thought that serotonin was the cause of depression. But research now has shown us that maybe that is an incorrect conclusion. So, what I want to do this whole semester is try to give you an appreciation for the critical thinking abilities to understand the difference between that which is demonstrably true and that which hasn't been demonstrated to be true just yet. So we're interested in science. Remember, in the last lecture I talked to you about this idea of science, and science is a process of observing and measuring things. There's probably an implied construct of truth, the search for the truth in these three things, and that's what we're going to talk about today. Okay. So now here's the question. A lot of people today are asking the question, should I trust science? And in fact, the famous Mark Twain made this very famous quote about statistics, which represents, if you will, a skeptical attitude towards science. And what I'm going to try to convince you of in the next couple of lectures is yes, you should believe in science if done properly. The only thing you need to worry about is scientists who do science improperly or do science fraudulently. Okay. So remember, and I want you to separate that out because I think science gets a bad name, and people today who are arguing about for and against different medical procedures or whatnot seem to get these two things confused. Science is an objective set of procedures. All right. It's not a person, it's not a microscope, it's not a thing. It's a belief in a set of procedures that allows for the observation and measurement of the world. It's nothing but a set of tools. Science may be wrong, but it never lies to you. It is always it may be incomplete, but it never lies to you. Science can be trusted. On the other hand, scientists are fallible human beings that sometimes do science improperly, or sometimes they have agendas and they use science to lie about their agendas. So let's differentiate. And what I want you to have here is a healthy skepticism of scientists, which is not a bad thing, but I want that to be based on an appreciation of what science, the tool, is. I don't want you to be one of those crackpots that out there saying, "Oh, science is all garbage, blah blah blah." No, but I do want you to be that critical thinking person who challenges a scientist to prove, to demonstrate what it is they are trying to, the theories they are trying to support. Okay, so we want to be skepticals, but not crackpots. So a real scientist is skeptical. They require proof. I want you to be skeptical and require somebody to prove something to you. And the more extravagant the claim, the more extravagant the proof. However, I do want you to be open minded. You know what? There is nothing wrong in saying that your knowledge was incomplete or wrong. A lot of people think that when science changes its mind, that it is somehow wrong. No, science is an incomplete process. You need to be willing to change your mind if the evidence comes in, no matter how you feel initially. And I think today a lot of people are really if you will, dug in to their beliefs, and they think that the change of beliefs is to demonstrate them as a problematic or a fallible human being. No, you have to be willing to change your mind if convinced. And the other thing is, there is no way for science to truly be objective. We, after all, are human beings. So, what I want you to do is to always go around armed with the knowledge of the biases that might be in your head as you look at this thing or that thing. Just realize that you have limitations as well. And don't be afraid to step outside of yourself and judge your judgment from another angle, if you will. And so the goal of this class, psychology in general, and me personally, is not only to teach you a little bit of psychology, but to make you a better scientist, a better consumer of knowledge, a person who knows the difference between good science and bad science. Okay? Now, and here's the deal. Belief in science is really just an attitude. Some people believe in science and some people don't. An attitude, if you look in the social psych chapter of this textbook, an attitude is a relatively enduring set of beliefs, feelings, and behaviors towards a given object. Think about your friends. Do any of you have a friend who has a very negative attitude towards science? Or excuse me, towards the COVID vaccine? Do any of you have a friend that has a very negative attitude towards the COVID vaccine? Maybe some of you have a negative attitude towards the COVID vaccine. I have an attitude towards the COVID vaccine as well. I won't tell you which way, but if you walk around today, you're going to hear people talking about the logic behind why COVID vaccines work or don't work, why they like them or don't like them, why they're going to get them and why they're not going to get them. In a sense, science, the attitude towards science is something that people feel, and you can think about it as being uh, controlled by the same forces that control every other attitude. So just like you have an attitude towards this sport or that musician, people have attitude towards scientific finding. Now, here's the problem. Most people's attitudes are not based on the facts. The research in social psychology shows you that people formulate good, thoughtful attitudes when they are given stuff that they are able to think about properly and that they care about. They have the ability and the motivation, right? Now, if people have the ability and the motivation, they typically think deeply about their attitudes. And what I want you to do is to think deeply about every scientific claim that is put forward to you. I want you to do that. But most people don't have the ability to process because they don't have the scientific expertise that you have. Instead, what they do is they resort to the peripheral route. They look at people who are on the TV channels that they like. They listen to the people, they listen to their celebrities that they like. And you know what? Nothing against Van Halen or Puff Daddy or Snoop Dogg, but they're not scientists. And if you are getting your scientific opinions from these people, you're using peripheral routes. You're looking at popular people. You may look at companies that you support and think blindly if that company likes this idea, that it is good for you as well. These are all peripheral cues. What I want you to do is having because you know what science is, you're going to use the central route to thinking about scientific claims, and you are going to be a better consumer of science. Okay, hopefully everybody understands what I'm talking about. Now, here's the deal. The details about science, you're going to learn them and you're going to take many classes. The most important part is what I'm talking about right now. I want you to have this attitude towards science. Most people fall into one or two camps. They totally reject science or they believe everything that comes out of a doctor's mouth. What I'm trying to suggest to you in these first two slides is you need to be better than that. You need to develop these scientific skills. Now, I'm going to provide you some websites and some other things to look at, and you can blow them off and pass this quiz and do just fine. But what I really want you to do is to care enough to learn a little bit more about these methodological tools so that you can become a more complex consumer of science. I see we've had a couple of people join the broadcast, and what I'm trying to do is to convince you to learn the rules of science so that you don't have to listen to what authorities say and you can go in and learn about research on your own. If you've just logged into the broadcast, please type your name in the chat bar and type a hello so I know you're here. I'm just interested in seeing who comes to these broadcasts. Okay, now here's the deal. Psychology in its broadest form is nothing but a circle of theories and hypotheses. All right. A theory is an explanation about why something happens. That's as general and as specific as I can get. Okay. Why is Dr. Roddenberry doing this broadcast? Well, he likes to hear himself talk. That's a theory for why Dr. Roddenberry does live broadcasts. Why did my friend steal my boyfriend or girlfriend? Well, because they're an awful person. That's a theory. A theory is an explanation of why something happens. And in science, science is basically nothing but a patchwork quilt of theories that all work together. And what we do is all these theories tell a story about how things work. Psychology, the book that we're looking at, is a patchwork of theories that, if taken together, draw a picture of what it means to be a human. A theory is simply an explanation of why something happens. An example of a theory, we might say, why do people have low self esteem? I'm sure you've met friends who have no confidence, low self esteem, right? Why do people have low self esteem? If you have an explanation for why people have a low self esteem, go ahead and type it in the chat bar. I'd be curious to hear what your theory of self-esteem is. But here's one theory, and I'm just going to throw this out here. It's not the right one, but it's just an easy one to talk about. We might say that people have low self-esteem because they don't have and they are lonely. They have low levels of social interaction and they feel lonely. Alicia says that people have low self-esteem because they are fearful of judgment. That's a great theory, Alicia. So Alicia and I have competing theories. I say people have low self-esteem because they're lonely and they don't have anybody to talk to. Alicia says people have low self-esteem because they have a fear of evaluation. These are two theories. Now, here's the deal. You never accept a theory unless the person demonstrates it to be true in the real world. A hypothesis is a specific test that you can do in the environment that should be true if your theory is true. Do you folks remember way back in middle school learning the definition of a hypothesis? Can somebody out there who's smart enough to remember what's that two-word definition you were given for a hypothesis somewhere in middle school science class? Does anybody remember that two-word definition? Come on now, I know somebody does. It's called educated an educated guess. Very good, Lauren. It's an educated guess. Do you know why it's an educated guess? It's educated by a theory. That's what they meant. They didn't tell you this subtle part. It's educated by a theory. If my theory is true, then this guess should turn out to be right. And the guess is the hypothesis. So if my theory is true, then what I should do is I should be able to go out to a group of people and I should be able to ask them how many friends they have and how many hours a week they spend talking to people. And then I should be able to give them a self-esteem questionnaire. And the people who have fewer friends should have lower self-esteem, score lower on that self-esteem scale. And the people who have more friends should score higher on that self-esteem scale. Now, Lauren Mahaffey, Alicia says that people have low self-esteem because of fear of judgment. How would we prove that demonstrate that to be true? Is there any kind of judgment that we could demonstrate and then combine that with a test of self-evaluation, right? Does anybody have a theory? What if we brought people into the laboratory and we had them take a test and we told some people you failed the test and you're not very smart. And the other people, after they took the test, we told them, hey, you did well on the test and you're really smart. Might we find a difference in self-esteem? Right? Now, here's the deal. What's happening is we have a general idea, but we have to test it in a specific situation. All right. Now, you see this circle right underneath me. what it's showing you is that this circle, you're going to develop a theory and you're going to test it with that hypothesis test. And that hypothesis test is going to say, yep, in this particular situation, our theory was true. And then you know what? You're going to evaluate that theory and say, wow, that theory is right. Now, if your hypothesis test doesn't come out right, you're going to revise your theory. So if your theory is right, you might add to it and try to make your theory more complex. If your theory doesn't show up to be right, you might change that theory. And so we've got this circle of always doing theories and hypotheses, theories and hypotheses. And so where do we get our hypotheses? We get them from the research literature, what's been done before. And we might have a research question, a problem we want to solve. So we have a problem that we want to solve, and we have some theory, the research literature. And that helps us create a theory, and we do the empirical study, and that tells us whether or not our theory is right. Now, here's the deal. I don't know if any of you have ever heard this, but there's no such thing as proving a theory. I don't know, you folks have probably heard one of these uneducated people say, well, uh, um, uh, evolution is only a theory. Evolution is only a theory. Evolution is only a theory. Yes, there is there is no a theory. Everything is a theory, and theories are never complete and never perfect. And so the fact that evolutionary scientists say yes, this is just a theory, and the fact that they change what they believe in every once in a while doesn't mean that evolutionary scientists aren't good scientists. It means they're great scientists. Evolution is just a theory. It's not a law. It's not perfect. Science realizes that there's no such thing as the last theory or the final word. And so the things that I tell you today that I think are absolutely true, in 50 years, I guarantee you somebody will have done research to demonstrate that what I'm saying today is not entirely correct. Okay? So, science is a set of tools. When done properly, it gives us an outcome which helps us learn about the real world. Our tools may sometimes not always tell us the exact truth, but our tools will never intentionally lie to us. And so, what we want to do as scientists, as psychologists, is learn about how the brain functions by creating theories and hypotheses. And as we learn more, we're going to develop better theories that help us learn more about the human being. Now, chemists do science, biologists do science, anthropologists can do science, anybody can do science, and anybody can do science poorly. It's a set of tools. All right. Now, that's enough of the convincing. What I'm trying to do is to give you an attitude. Now, here's the deal. If you are going to have this scientific attitude, my friends, you hear me? You cannot do Google and think that is research. You can't listen to a Joe Rogan podcast. You can't look at Jordan Peterson. You can't go on the BBC or TikTok. Now, these are all great ways to hear nuggets of information, and I'm not going to down any of those things. In fact, sometimes I use Wikipedia as a shorthand, and sometimes really interesting factual things come across TikTok. But if that's how you're building your knowledge, you are not being a good scientist. If you really want to learn, what you have to do is you have to go to the scientific journals and learn how to act just like a scientist does. If somebody's going to make a claim on the news, you need to find their scientific article and read the doggone article yourself to see if they did the science right. If they did the science right, then you may have to accept what they say. But what you're going to find is a lot of people are going to make claims. And if you look at their original research, you'll see that their science has problems. Okay. So if you want to learn about breast cancer, if you want, I had a little cancerous tumor several years ago and had to have radiation therapy. I didn't go to Google. I actually went to PubMed and downloaded all the scientific articles about my type of cancer and the treatments. And I read the exact scientific articles. Now, in order to do that, if you've ever read a real scientific article, they can be difficult at first. You have to, they're written in a really weird language, a scientific language that not everybody's familiar with. They're not smarter than you, they're just using a lab language. And what you as a consumer have to do is have to read enough of these articles to understand what lab language is like and what they're talking about. Now, a good start for you, real quick, is to know what goes in a journal article. If you were to get an article out of PubMed, a medical article, or go to the APA and get a JPSP, a Journal of Personality and Social Psych, or a Cognition, or the journal Nature or Cognition, you're going to see that all papers are written in a general structural order. Now, you folks as freshmen are learning MLA style, and that's the structural organization that you use to write English papers. Well, psychologists use APA style, and that's just the way that psychologists are supposed to write their papers. And APA style is similar to all of these research paper styles, and it's going to have 6 general sections you need to be familiar with. Okay, so in the introduction part of the paper, and it's usually all of these sections are going to be labeled methods, results, discussion tables, and appendix. The only one that doesn't get labeled is the introduction. It's because it's the first one, so they usually just put the title. But basically, if you look through these papers, you can find the different information. So if you want to just see what the data are, you know where to look in the paper to just find the results. If you want to see where the person got their hypothesis and theories from, you'll know you just look in the introduction. If you want to see how that person measured this brain thing or that brain thing, then you know you just go to the methods section. So by knowing what's in the paper, you know where to look in the paper to find the information. This makes it easier for scientists to read a paper because the paper is structured such that they know where all the important things they're looking for are. So when you write a journal article, you're going to use this organizational strategy right down here. In the introduction, you're going to describe the research and where you got your theory from, okay? What are all my background sources? What research did I use that led me to this to this theory? And what hypothesis do I want to test in this study? Then in the second part of the paper, you're going to tell me whether or not you did an experiment, a correlation, what kind of scales you used, what kind of blood tests you did, what kind of machine you used to measure people's brain. You're going to tell me what your methods were. In the third part of the paper, the results, you're going to show me, you're going to tell me what you found, what kind of statistical tests did you do, and what kind of results. Did they support your hypothesis or not? Now, it turns out that there's a lot of deception and lying in research these days. Remember, I talked about on slide 1, trust science, but not scientists. And there's been a movement in the last 10 years to force scientists to turn over their data along with their results. And so you actually have to turn in the spreadsheet, the Excel file with your results that show how you got to your results. Did you know there are actually organizations out there that go around looking to see if they can catch scientists lying about their results? Unfortunately, it's a big problem in science, folks, and it's why people don't trust scientists because their results are often faked. And so you want to look at the results and you're more often to believe in scientists and journals where they require the scientists to also publish their data set too. So in some journals, you can read the article and get the actual data that the scientists used to write the article. And those are the journals where the stuff that's least likely to be a lie can be found. Okay. Again, we're being good scientists. We're being good consumers of science, right? Now, everybody following me, if you're following me, go ahead and type in the chat bar and let me know you're there. Okay. Just so I'll know that everybody's there. All right. And so your results are where you publish what you found. Okay. And then in the discussion section, what you do is you talk about what's my next step. If you supported your theory, then you make your theory even more refined and you add to your theory. If your data don't turn out, then you change your theory and talk about how you might change your theory. And then in the back, very back of the article, if they have tables or graphs, a lot of times if you have complex data, what you'll do is provide charts, maybe pie charts, line charts, whatever. So you'll see those in the back of the paper. And then if the person is using a new research tool, let's say I've created a new questionnaire, what you'll usually do is you'll find that at the back of the paper. So if you were to do read a research paper on self-esteem, at the very back end of the paper, the author should give you a copy of the self-esteem questionnaire that they actually used. And see, here's the deal. This is why you don't want to Google or use CNBC or Fox News or any of those people, because they're not giving you all of this. This is the whole story. I know what research you're coming from because I read your introduction. I know that you did the test right because I read your results. I actually see your data set and see your results. I can trust that. And then you explain to me what the next step is so I can integrate this into what I already know. And if I want to look at your questionnaires, I can see them. This is the gold standard, this research paper. And what you have to keep in mind is that medical doctors are paid by drug companies tons of money. Psychological researchers have agendas. Politicians have agendas. So it is very important that you learn how to look and notice all of these things. Cool? Everybody following me so far? See, here's the deal. I am not going to tell you what to believe in this class. I'm going to give you some theories, but I'm never going to tell you to be a conservative, to be a liberal, to think this about about this sexuality or that sexuality. My goal is not to tell you one thing to believe. Instead, my goal is to give you a set of tools so that you can do the thinking on your own. That's what frees us from the man. You know what I'm saying? Okay. Now, let's go back to the second part, the research methods. This is the key. And this is where you really need to learn how to pay attention if you're going to discern between good science and bad science. Sometimes you can do science poorly, okay, and that's a bad thing. But sometimes you can do the right kind of science, but then draw the wrong kinds of conclusions for it, okay? There are three different broad ways to methods that can be used in science: the descriptive method, the correlational method, and the experimental method. And here's the key. There are different conclusions you can draw from these types of studies. So you can do a bad descriptive study, and that's bad science, or you can do your descriptive study right, but draw the wrong conclusion from it, and that's bad science. You can do a correlational study poorly, and that's bad science. But you can also do a correlational study properly and draw the wrong conclusion from it, and that's bad science as well. And it's the same thing with the experimental method. You can do a bad experiment, and that's bad science. Or you can do a good experiment, but draw an incomplete or an incorrect conclusion from it. So we need to know how to do these three methods correctly, all right? And then more importantly, we need to know when they should be used and what kind of conclusion we should, excuse me, I got the hiccups, we should draw from them. Okay. Now, descriptive methods, they're simple observations. They're good for preliminary research or unique situations. You know what? Although they are used in other forms of research, but descriptive methods are one way where we just go out and we observe the environment, we observe people, we observe situations. Descriptive research methods. It's nice to set up since it's easy to set up and it doesn't require as much control over the environment. It's a great way to start research. And you'll notice that I'm going to talk about 3 different ways you can do it. You can do just general observational studies. Dian Fossey went out in the jungles of Africa and would just watch apes play around, okay? Or you could have people tell you about themselves by filling out questionnaires, or you could find a unique person. So we have different description methods. And then there are correlational methods where we look for relationships between variables. And have you ever heard that the more you smoke, the more likely you are to get lung cancer? That's a correlational study. That's correlational research right there. People who smoke more cigarettes are more likely to report cancer later in life. And then there are these things called experiments. And all of you have heard of experiments, but this is the trickiest part. Experiments are the easiest, they require the most control, and they are the situation where it's easiest to make a fundamental research mistake. However, an experiment that is done well allows you to do this really cool thing to say that you believe that A causes B. And causation, if you really know how something works, then you can predict what's going to happen in the future because you understand the causal link. Hopefully, everybody understands me. Okay, now I'm expecting you, I've provided links. We're going to go over these 3 methods fairly quickly, but here's the deal. I'm going to expect you to understand these in detail, and I've provided links where you can go get the research, the knowledge on your own. I'm providing the overarching structure, and you can go in and read the details. But I want you to understand what the different types of descriptive studies are. I want you to be able to identify when you move from a descriptive study to a correlational study, and I want you to know the important difference between a correlational study and an experimental study so that you can identify them. So you're going to have to learn the details in a sense on your own. I'm going to quickly spend 15 minutes talking about them, but I hope that you can follow up and really sort of fill in the missing pieces. This is an online class, so what I do is I give you the basic structure, and you kind of have to do a little bit of self-teaching on your own, okay? So this is the organizational structure. Now what I'm going to do is I'm going to talk about these 3 different methods, descriptive, correlational, and experimental methods, and maybe even provide you an example or 2. Okay? So descriptive methods, sometimes you just observe. Simple observation is good for preliminary research or unique situations. Be careful though, these methods do not allow us to draw firm conclusions about cause and effect. I don't care what happened to your cousin. That doesn't mean that that's how the rest of the world works. How I was sitting in a bar the other day, and a gentleman was telling 2 other guys that his cousin got the COVID vaccine and 2 months later developed this disease. And this guy was positive that that was proof that that this COVID vaccine caused his cousin's disease. And whoa, I mean that you can't do that. Observations are great. They get us on the trail to sniffing something out to see if it is true, but they are not going to allow you to say anything about cause and effect. They are simply observations. Look around today when you get on social media and notice most of your friends are going to be basing their scientific logic and their scientific opinions on simple observations. This happened. This trucker did this. This guy's on TikTok saying this. This happened in this situation. Those are simple observations. You can't draw conclusions from them. Okay. Now, in science, we talk about descriptive methods a little more specifically than what happened to Uncle Ted. We talk about maybe case studies, naturalistic observations, and laboratory observations. Now, Diane Fossey and people who study wild animals go out into their environments and take notes about these environments. That's a naturalistic observation. You can do the same thing for people. You can go out to a political rally. You can go out to a baseball game. I saw a guy give a talk who did an observational study in the men's bathroom at a college campus. He wanted to find out how good college students were at hand washing behavior. Spoiler alert, they're not very good, men or women, at washing their hands after they go to the bathroom. Ugh. But it was simply a naturalistic observation, how people are behaving in their environment. Sometimes what we'll do though is we'll bring people into the laboratory, give them a set of activities or things, and just let them interact naturally. Now, in a sense, this is still an observational study because I just got them in my laboratory and I'm not telling them to do anything, okay? But the fact that they're in my laboratory might change their behavior just a little bit. So whenever you see somebody do a naturalistic study, ask yourself, were they doing a study where the people were in their natural situation and didn't know that they were being observed, a naturalistic observation? Or did they bring these people into a setting where these people knew that they were being looked at, a laboratory observation? Now, one of the famous laboratory observations in the field of social psychology or developmental psychology, both really, would be Mary Ainsworth's strange situation study, which is where she would bring mothers and their toddlers into her laboratory. And then over the course of 15 minutes, she would cause the children to be separated from their primary caregivers, 1960, so it was mostly their mothers, over several times over a 15-minute period, and she studied the way these children reacted to being separated from their mothers. A very famous laboratory observation. You know, probably one of the most famous case studies. Now, the coolest thing in psychology are case studies. And case studies are really where we've learned an awful lot about how the brain, the neurological foundation of human functioning works. And probably one of the most famous case studies in the whole world is a fellow named Phineas Gage. You should see this picture right here. Phineas Gage was a railroad worker in the 1800s working in upstate New York. And he was tamping down some TNT explosive with a metal rod, and it exploded and sent that rod up through his head, just like you see here in this skull picture. You know, here's the crazy thing. It went right through his head too and went 20 feet in the air. Here's the crazy thing. Phineas Gage never even lost consciousness, never lost consciousness. He fell down and he was stunned, but he never passed out. 3 days later, Phineas Gage was up and walking around and was, by all intents and purposes, he was completely normal with one change. His personality completely changed, and he became an argumentative braggart that liked to fight with people. The most famous case study in the world. And so Phineas Gage led us to begin believing that personality was controlled by this front part of the brain. I don't know if you've ever heard about children. Little toddlers can't sit down and be quiet. We know it's because this front part of the brain is responsible for controlling your impulses and your temper. And it was destroyed in Phineas Gage. Now, later scientific studies would show beyond a shadow of a doubt that that's what the part of the brain was for. This interesting case study led us to begin developing a theory of which part of the brain controls personality. Over the course of the semester, I'm going to show you several different, what I think to be really interesting and classic case studies that demonstrate fundamental points about human beings and human psychological functioning. However, one thing you need to keep in mind is that you can never, ever, ever draw a causal connection from a case study. You can't say that just because this happened to Phineas Gage, that this is going to be the same for everybody. You can never draw that conclusion from a case study or actually even a naturalistic observation. These kinds of studies, you can't say A causes B. Okay, you just can't do it. I don't know if you folks know this, but language, the ability to talk, is controlled in the left side of the brain for 90% of all right-handed people. You know what that means? If you were to damage my brain over here, and I am one of those 10% of those people, you might say that language isn't controlled by this part of the brain, right? You may have the person who falls in that 10% and has language on the other side of the brain. Each brain's unique and different. So just because you learned about one brain or one person doesn't mean you can necessarily generalize. However, case studies and observations are great in the initial parts of the research to say, you know what, we need to do further research in this area. Here's the problem, folks. What you're going to find is that a lot of people are going to do a case study or a simple laboratory or naturalistic observation, and then they're going to say, see, look, this is proof that A causes B. A causes B. You can't do that. You can't do that. You can't do that. All right. You can't do that. All right. But what you're going to find is that people will jump the causal gun using a case study or an observation. Okay. And you know what? As it says, so there you go. Now, correlational methods. Now, that was the first, the descriptive method. Descriptive methods, we typically go in and measure one thing. Okay, I'm going to measure this person's behavior, or I'm going to measure the way they feel, or I'm going to measure the way they think. Correlational methods start to try to put things together by showing that things tend to be related to one another. Okay. So one of the things we know is that the more that you talk to a baby, okay, the earlier that baby will begin to talk and the better their language skills are. And in the research, what they do is they'll go out and they'll ask 1,000 new parents. They'll say, okay, how much do you talk to your baby? Estimate how many hours a day you talk to your baby. And the parents will say, well, I'm really busy, so I really only talk to my baby an hour a day or 2 hours a day. Other parents will say, you know what, I incorporate the baby in anything and I talk with the baby 18 hours a day. And so what you can do is you can ask parents to tell you how much they talk to their baby, or you can even put a camera in their house and measure that. So you can measure that variable. And then what you can do is you can then you can measure that child's vocabulary at 5 years of age. You can figure out how many words they know, or you can measure how young they are when they say their first word. Okay, and so what you can do is you can measure these two things. And a correlation shows you if two measured variables change in any kind of a pattern. Okay, so in what I've described to you, I'm suggesting that the more you talk to a child, the bigger their vocabulary is. Notice how I use two comparative words. The more you talk, more as so some people talk more, some people talk less. So there's an amount you can talk. And then the other thing I say is the larger your vocabulary, suggesting that some people can have bigger vocabularies than others. What I can do is I can measure those two variables. And then I can create a scatter plot where each person gets a vocabulary size and an amount of number of hours that their parents talk to them. And I can create a scatter plot. And this scatter plot can begin to show me if there is any sort of what we would call linear relationship between these two variables. So what you might see is the more hours I talk to a kid, the bigger their vocabulary. That's what we would call a positive correlation. Okay, okay. On the other hand, what we might find out, the parents might tell us, if I work a lot, I can't talk to my child. You know what I might do? I might say that parents who work a lot have children with smaller vocabularies. So I could come in and I could ask you how many hours a week you work, from 20 to 70 hours a week, and then at age 3 I can measure your kid's vocabulary. And what we might find is the more hours you work, the lower your kid's vocabulary is. That's what we would call a negative correlation, because as the hours go up, the vocabulary size goes down. Okay? And so what we can do is we can establish a directional relationship between two variables. We can show that one variable goes up as another variable goes down, or one variable goes up as another variable goes up. That's what we would call the directionality question. And correlations can either be positive or negative. The number of hours you spend, what research has found, the number of hours that a student spends in a course shell, the higher their grade is in that online course. Duh, right? Okay, now the second thing you need to know about correlations is you can also sort of estimate how strong that relationship is. I want you to look at the charts over here. Look at 1.8, 0.3. And what I want you to notice is that in 1, a strong positive correlation, you can draw a line that almost completely covers those dots. That's a strong linear relationship. Actually, that doesn't exist. You'll never see that in nature. What you will see sometimes is what we would call a moderate positive correlation. Now, I could draw a line. You can see how these are kind of in a line shape, but if I draw a line, it's going to miss some of the dots, although it's close to most of them. That's a correlation that's not quite as strong. And then if you look at 3, what you're going to find is that, yeah, I could kind of see, maybe I could draw a line, but those dots are kind of spread out and they don't really show necessarily any relationship. And if you look at 4, no correlation, you can see as one variable goes up, the other variable doesn't do anything. And then going down the other side, it shows you 3 examples of negative correlations. Now, what you should notice here is that direction and strength are 2 different things. So you'll see both a strong positive and a strong negative correlation can both be a 1, but one of them is a negative 1 and one is a positive 1. Those are both equally as strong, but one goes in the positive direction, the other goes in the positive negative direction. So correlations, sometimes what you're going to find is people are going to go out and say, look at this, the number of, we should give people more daycare, because what we find is the more children go to daycare, the higher their test scores are and the fewer behavioral problems are. Somebody's gone out and measured the number of hours a kid spends in daycare and behavioral problems, and has made that sort of that statement of correlation between these 2 variables. So you can go out and measure the relationship between different things, and then you can suggest that those things are related. However, here's the deal. Correlation does not mean causation, okay? And what you're going to find, this is the even bigger problem. A lot of people are going to do what are essentially correlational studies and then call them causational studies. Now, here's the deal. You might say that if the more hours you work, the more behavioral problems your child's going to have. You know what? You might say more work causes behavioral problems, but maybe I work more because we are poorer. So is it the fact that I work more or I have less money that causes the behavioral problems? I don't know. Is it because I'm less educated? Maybe the reason I work more is because I have less education, so I make less money, so I have to work hard. So really, you can't tell me that working causes behavioral problems any more than you can cause me poverty causes behavioral problems, or lack of education causes those. Because what you haven't done is you haven't isolated any one of those factors. In order to do that, you need to do an experiment. And in an experiment, what we do is we use random assignment. Random assignment. Okay? Now, here's what I could do. Okay? What I do is I bring in a group of people and I randomly put them into two groups. All right? Now, let me give you an example. There are 36 people in this class. Let's say I brought all of you in all of you are different heights. If I brought you in and randomly closed my eyes and did 1, 2, 1, 2, 1, 2, and put you into two groups, and then measured the average height of those two groups, okay, you know what would happen? I would probably have two groups that are similar in average height. Does that make sense, folks? Type yes in the chat bar if that makes sense to you. And that's what I did was I randomly assigned you into two groups and you had an equal chance of being in every group. Now, if I then compare those two groups and they change, I can say that change is due to something that happened after I assigned those two groups. Now, what if I decide to do it this way? What if I bring you into the laboratory and instead of randomly putting you into two groups, I put all of the females into this in one group and all of the males into the other group and measure the average height. Are those two groups going to be similar? What do you think is going to be the relationship between those two groups? Are they going to be similar? Are the women going to be taller on average, or are the men going to be taller on average? Question, question, question. What do you think? What do we know? It turns out the men are definitely going to be taller, right? Because that's just typically in species, the male of the species tends to be bigger than the female of the species. Yes. All right, now here's the deal. In the first situation, what I'm going to do is I think I have this growth hormone that causes people to grow tall. So in the first experiment, you know what I'm going to do? I'm going to break these two groups up and I'm going to give them and I'm not going to measure their height. Okay, but I'm going to randomly assign them. I'm going to give them the growth hormone. And what I'm going to find is after 6 months, these two groups are still similar. These two groups are similar in their height. Does that growth hormone work? So I randomly divide my classroom. I don't measure how tall they are. I could if I wanted. Okay, but I don't. Let's say I don't. And then I give them the growth hormone. And at 6 months, I find that both groups are still the same height, right? You would say the growth hormone doesn't work. Now, I'm going to take two groups of people, but I'm a bad scientist. So instead of doing that, what I did was I took all the ladies and put them in this group, and I took all the men, and I said, you know what, I'm going to give the growth hormone to the men. And after 6 months, what I find is that the men are taller on average. Does my growth hormone work? No, it's because my groups were different at the initial time. So in a true experiment, what we do is we get a group of people and look at the researcher's methodology. Make sure they randomly put the people into the groups that they're comparing. This is where the big mistake occurs. This is where most scientists get it wrong, or most pseudoscientists get it wrong. You have to put them into the two groups that you're comparing using random assignment. There's a link over here that'll show you what the difference between good and bad random assignment is. And then what you do is you do some sort of manipulation or training on the two groups, the independent variable, and then you measure the two groups. And if the two groups are different at the final, they were similar at the beginning, different at the final, and the only difference is the independent variable, then you can begin to say that A causes B. And what I'm going to do this semester is I'm going to show you a couple of experiments where they bring people into the laboratory, randomly put them into two groups. And then what they're going to do is they're going to alter the situation for these people in one important way. And then they measure how those people react. And then what they do is they build a theory saying, well, this environmental thing causes people to behave in this particular way. Okay, now what I want you to do is I want you to read on your own about random assignments. I want you to read about blinding, which is we don't want the experimenter to know what the results are supposed to be, and we definitely don't want the participant to know what the results are supposed to be, so that they will act naturally. Okay, and these are all characteristics that will help you make a good experiment, so that you can begin to say that A causes B. Now, I'm going to end this broadcast by telling you again, here's the problem you're going to run into every day. You're going to run into it today. I guarantee you. You're going to get online and somebody's going to make a causal claim. This is causing that. This is causing that. This thing that we're doing in schools causes this to happen to children. This kind of thing that happens in movies is doing this to women. Everybody's going to be making a causal claim, but very few people are actually going to do a true experiment in order to support that causal claim. You, as a good scientist, are going to learn how to, and one of the things I'm going to ask you to do in this class is to learn how to differentiate between a descriptive study, a correlational study, and an experimental study, how to know when they're done properly, and how to know what conclusion you can draw from these particular studies. Okay? And the whole thing is, I don't want to convince you of anything in this class. I instead want to give you the tools to find out the truth on your own. That's what education should be. All right? Does anybody have any questions? Please ask me a questions or type hello in the chat bar, or type goodbye, or type, wow, what an awesome lecture. I'd prefer you ask me a question. Okay, wow, that is lecture 1. Now what we're going to do in the next class is we're going to talk about IQ testing. And what I'm going to talk about with IQ testing is how this research method has sometimes been used improperly to the harm of science and society. Okay, well, there are no questions in the chat bar. I don't see anything in the chat. I'm sorry, my screen's gone down for a minute. I hope everybody, let's see what we got. Nothing in the chat bar. Okay, cool. All right. If you folks do have any questions, don't hesitate to send me a text. Otherwise, I look forward to seeing you next time. Take care, folks. Bye.